Okay guys, in this video we're going to continue to look at solving trig equations, but trig equations that involve a little bit more algebraic technique or maybe additional steps. So let's go ahead and start by considering number 7 here. If I were to ask us to go solve sine 2x equals a half, this is an instance where we say we would have what we call a multiple angle. And the reason why is because, at least in our last example of solving equations, we looked at solving trig functions where in the angle it was just a variable. And in this case we have a coefficient on our angle in there, and so we would call that a multiple angle. We're going to solve it using similar techniques, that is, try to isolate the trig function and use an inverse trig function to undo it, but it also means that we're going to have to take some additional steps once we proceed a little bit into this, okay? The only other difference about this one from the previous two we looked at is also going to be that I want to use the steps outlined on the first page to find all solutions to the trig equations. And so that is to say that there aren't just the ones that are between 0 and 360 that land here, but let's say 30 degrees is a solution, then so would be 390, just because I could tack 360 degrees onto that. Or basically 30 degrees plus any amount of 360 degree rotations would be a solution if 30 degrees is a solution. And so we're going to write our solutions this way. We would say solution, or I guess our angle, at least I would write for our solutions here. So our angles equals solution plus period times n or k. In other words, we're just going to add on the period of the function because we know that's how much angle input we would have to go through before it starts to repeat itself again. Okay. So taking a look at number 7 here, let's take a look at the steps I would take to do this. I notice that it's not a very complex statement. I need to get sine by itself, and it looks like it's already by itself on the left-hand side. And so using our steps here, we're going to take the sine inverse of both sides. If I take the sine inverse of the sine of 2x here, I have to take the sine inverse of everything on the right, which is a half. What happens on the left is that I end up saying that 2 times my angle is equal to the sine inverse of a half. Now here's the thing. With respect to this, we're still going to go look at sketching this out here. I notice that sine is positive a half. And so the very first thing we want to do is ascertain to which quadrants we would be isolated. We would say that I couldn't be down here if sine is positive. I have to be angles up here. And the next thing we would try to do is to ascertain the reference angle. Where would sine be a half? Now I sketched this out in my last video, but our sine values being a half would be a half at a 30-degree angle. And in this case, are we doing degrees or radians? Let's go take a look here. Looks like that we are doing this in radians. And so in terms of a 30-degree angle, we would also call that a pi/6 radian measurement here. So it has to have a pi/6 radian reference angle, and it has to be in the first and the second quadrant here. So we're going to say that this is pi/6 and that those two angles are the same. So what are the actual angles in standard position? Well, one of them would just be pi/6. But keeping in mind that this would be 6 pi/6 here, and we're a pi/6 short of that, this angle here would be 5 pi/6. So the difference between solving this equation now and solving the last equation is that we just determined that the angle solutions were pi/6 and 5 pi/6, generally speaking here, between 0 and 360, but this time we have to do plus their period times n. So in this case, what I'm going to do is I'm actually going to write them off on the side, and I also have to take into account that this is 2x that we solved for. I'll write it over here. I say 2x equals pi/6 plus the period of our sine function times n. Now what's the period of sine? Well, the period of sine is 2 pi. Remember that the period of all of our trig functions except for tangent and cotangent is 2 pi. Tangent and cotangent have period of just pi. So we get 2x equals pi/6 plus 2 pi n, but we also got 2x equals 5 pi/6 plus 2 pi n. So that final step that we have to take now is actually to go back through and divide everybody here by 2. And just to make it a little bit easier for you here, we're going to divide both parts of these numerators by 2. When you divide this fraction pi/6 by 2, it's going to be the same as multiplying by the reciprocal. So pi/6 times a half would be pi/12. So in this case, we would get x equals pi/12 plus 2 pi n over 2 is just pi n. And we also get x equals 5 pi/12 plus the very same pi n. And these would be all possible solutions right here. So a little bit different than finding standard solutions. We have to put on or attach on plus period times n. And then we also always have to divide by the coefficient of our angle if we have a multiple angle. Okay. So let's take a look at these equations down here. And you'll notice that I already titled these equations that require factoring. So sometimes in order to solve these trig equations like you're seeing here, we're going to end up having to factor, because looking at, say, numbers 10 and 12 here, we have like a sine squared and a sine to the first. It's just really impossible to isolate sine just by manipulating terms. We're going to have to factor this here. So taking a look at number 10, one thing that I want to point out is that the instructions say we want to list the solutions in radians and on the interval from 0 to 2 pi. And so we don't need to find all possible solutions here. Okay. Also, looking at number 10, I suppose that we're going to treat this much like we would an expression like this, 2x squared minus x minus 1 equals 0. That is to say that they're both kind of in the same form. It's just that we have sine of x that's being squared instead of x, and we have a sine of x instead of an x here. So in terms of factoring it, would factor much the same way. I tell people sometimes, hey, maybe rewrite this with just a variable instead of your trig functions here, if they're all the same type of trig function, and then try to factor it. So something like this, I would, of course, since we're undoing like a FOIL here, start with your f. I would say I'd have to have a 2x and an x here. They would have to multiply out to be this first term. So now that I have those, what could I put in the last spot here and here that would multiply out to be a -1? I could put like a +1 and a -1. Now in terms of whether or not this works, that's where we check our O and our I. Recall that that is just multiplying your outer. I would get -2x, and then your inner, I would get a +1x, and when I add those together I get -x. That would be beneficial because I do need a -x as my middle term's value. So this would be our factoring pattern. Well, when you look at something like this, that means then instead we're going to have something that looks like this: 2 sine of x in front, and then sine of x. So I would start by still getting my f part here, still trying my last part, which in this case I am going to adopt the same scheme I did over here, but +1 -1. But you could check your outer and your inner also, and we'd have -2 sine plus a +1 sine as a -1 sine in the middle. So the neat thing about being able to factor these, of course, is that if I can say that two factors multiply out to be 0, then either the first factor had to be 0, and so I'm going to go ahead and set that equal to 0 here, or the second factor had to be equal to 0, and so I'm going to set that equal to 0 over here. And we're going to solve these individually. Okay, so let's start with this on the left here. I suppose that we would want to isolate the sine value. So this would involve, whoops, I'm going to set it equal to 0, you guys. Subtracting 1 from both sides, we would have 2 sine of x equals 1, -1. And then we would have to divide both sides by a 2. So we really end up with this statement here, sine x equals -1/2, which leads us, or implies the statement, x equals the sine inverse of -1/2. And so I've solved that. I'm going to put a box around this and come back to it in a minute. Let's go ahead and isolate the sine value here. I would have the sine of x equals 1 if I were to add the 1 to the right side. So we really get x equals the sine inverse of 1. So I'm going to go ahead and start with this bottom one down here where sine is negative. And so what I would see is, and I'm sorry I don't have a lot of room here, but if sine is negative, we had to terminate either in the third or the fourth quadrant here. We couldn't have been up here or here. And in terms of where is sine 1/2, we're looking at reference angles here. I suppose I'll go back to my first videos here. Sine is 1/2 at a pi/6 reference angle. And so what that means is when we draw on these two angles over here, we know that the angles that it's making with the x-axis, both of these here, are pi/6 reference angles. So in terms of what our angles would have to be here, let me try to write that a little more cleanly, pi/6 here. That would mean that I'd have to be 1 pi/6 past 6 pi/6. So that would mean I'd get 7 pi/6 would be one of my solutions. But at the same time, I'd be 1 pi/6 short of one full rotation, which would be 12 pi/6 all the way around. So I would be at 11 pi/6 as two of my solutions here. Now those are only two of my solutions. Now I need to go look for where sine is equal to 1. Now on the unit circle, I didn't put that in over here on this first one, but where is sine equal to 1? Whenever you get 1 or 0 for your trig function values, it means that we were at one of our quadrantal angles. In this particular case, sine is 1 at 90 degrees or pi/2. And so that's going to be where I list my last solution here. We would say at pi/2. Now normally I would write all these together more cleanly, but we'd say these are all of the angle solutions to that particular equation. Now let's go take a look at this number 12 here, a little bit faster than the last one. One thing really quickly that I have us do before we start, just because I noticed I spotted a mistake, is to make this constant back here a plus. That way we have something that factors. But this looks like something that could factor. And again, I'd kind of just do some guess and check in terms of factoring, but I know that we're just kind of reverse foiling here. So up front, I would have to have a 2 cosine x times a cosine x. That would have to be the case. And then in the back, to multiply out to be a positive 1, I could put something like plus 1 plus 1 minus 1 minus 1. In this case, I'm going to go with plus 1 plus 1 just because my middle term has to add up to be a positive. And checking our outer and our inner here, we would get 2 cosine times 1 is 2 cosine, and 1 times cosine is 1 cosine, and 2 cosine plus 1 cosine is 3 cosine. So these are indeed our factors. Again, like we did last time, we're just going to take the time to set each individual factor equal to 0. So either 2 cosine x plus 1 equals 0. Either that's the case, or in this case, cosine x plus 1 could also be equal to 0. So we're going to isolate, get that out of the way here. We're going to isolate the cosine function in each of these here. So here I'm going to subtract 1 from both sides. So I get 2 cosine x equals 1, negative 1, and then we'll divide both sides by a 2 here. And so we would get cosine x is negative a half. And then it follows that x is cosine inverse of negative a half. So I'm going to box that, and we'll come back to it in a moment here. We could also see that if I subtract 1 from both sides on this equation here, we would get the cosine of x equals negative 1. And then it follows also that x is cosine inverse of negative 1. I'll put a box around that. So now, looking at this first one here, I suppose that this is going to occur at either 30, 45, or 60 because we're getting a value that's not 1, negative 1, or 0. And so where is cosine even equal to a half at in the first place? Well, looking at our cosine values, that has to happen at a 60-degree angle or a pi thirds. So that's what I'm going to use here. I'm going to use pi thirds reference angles, and it would also have to be in the quadrants where cosine is negative. And so that would have to be either in the second quadrant or the third quadrant here. But these are the two angles we're looking for right there and there. So because we know the reference angle is a 60 or a pi third right here, it's a pi third reference angle, then our actual angles would have to be 2 pi thirds and 4 pi thirds for this here. So I'm going to write 2 pi thirds are the solutions here, and 4 pi thirds, I would totally give it more room if I had more room, but there's 2 of our angle solutions here. Now in terms of the last solution, we have to find where is cosine equal to negative 1. Well, on our unit circle, the x value is only ever negative 1 at one angle, and that's over here on the left, and so this has to be a pi radian measurement here, or 180 degrees. So we would say that this is pi. And so our 3 angle solutions are these 3 right here. And so for number 14, this last one, we still want to factor on this one, but you'll notice that it doesn't look like it's in quadratic form. And at first, a lot of people probably get a little frustrated with the fact that we have cosine and sine involved here. But if you look at this as I have a term minus another term, what is it that I could factor out of both of these? Well, we always check for a GCF first. And so in this case, I could factor a cosine out of both. What that ends up giving us is cosine x out in front, and we get left with 2 sine x on the inside minus 1 equals 0. Now in this case, this is pretty neat because see, now we have 2 factors that multiply to be 0. So in the first, equation we could set up, we're going to set this first factor equal to 0, cosine x equals 0. Or in other words, the angle must be the cosine inverse of 0. And I'll box that. Or it is the case that 2 sine of x minus 1 equals 0, which I'm going to go a little faster on this one. If I were to add the 1 and divide by 2, I would basically end up with then the sine of x equaling to a positive a half, and it would follow that x equals the sine inverse of positive a half. And so, boxing these, let's start with where is cosine equal to 0? Well, between 0 and 360, this happens twice. Cosine is 0 up here at a pi halves, but it's also 0 down here at a 3 pi half measurement. So we're going to go put those both on as possible solutions here. So we would say that this happens at pi halves and at 3 pi halves. So where is sine equal to a half? Well, this one we're actually going to have to sketch. And if sine's positive, that would mean we'd have to be up in either the first or the second quadrant here. But with respect to what is the reference angle, let's go back and look. Sine is a half at a 30 or a pi 6 reference angle here. So let's go ahead and go back over here and acknowledge that both of these angles here are a pi 6th. So the angles in standard position that go around here are going to be pi 6th, but also 5 pi 6th. And so I'm going to write that as x is pi 6th and 5 pi 6th here would be our 2 solution angles there. But for the total solutions, it'd be all 4 of these angles together. Cheers.